everyone, welcome back to my channel. In the previous video, we successfully completed the numerical simulation of a 3D wing, verified its basic aerodynamic performance, and calculated the lift, drag, and moment coefficients of the entire aircraft. In today's video, I'm going to dive deeper into the simulation results. I'll walk you through two key parts. First, how to fully visualize the aerodynamic loads, including a very practical technique for generating wall streamlines. Second, and this is the most important part, how to export the correct data for the upcoming FSI analysis in a back use. This applies whether you're working with a simplified beam model or a full, detailed wing model. First, aerodynamic forces are mainly composed of two parts: the pressure acting normal to the surface and the shear stress acting tangentially along the surface. This is the pressure coefficient distribution on the wing surface. You can clearly see the high pressure stagnation region near the leading edge, as well as the strong suction region on the upper surface. To analyze the results more quantitatively, we used an XY plot to extract the CP curves at different span-wise sections of the wing. However, star CCM cannot display a true 3D plot, which causes all the CP values of a section to be collapsed into a single vertical line. By switching to Python, we can correctly visualize the CP values at different chordwise positions for each section. This makes it easy to observe how CP evolves from the wing root to the wing tip, especially after applying sharpening and twist modifications to the tip. Aside from pressure, the friction forces generated by the viscous flow are also significant. Here, I've switched to the contour plot of wall shear stress. This shows the distribution of shear forces across the entire wing surface. Using the CF plot, the skin friction coefficient plot, together with the Screen 2D results, we can clearly observe how the airflow attaches to the surface. If the shear stress drops sharply and approaches zero in certain regions, it usually indicates the onset of flow separation, something that is very useful for evaluating stall characteristics. As you can see, with a maximum flow speed of 50 meters per second, the overall magnitude of the pressure acting normal to the surface is much larger than the wall shear stress under such low speed conditions. Next, I'd like to share a visualization technique that I personally find very useful. Typically, we generate streamlines using the velocity field, which helps illustrate the flow pattern around the wing. However, when analyzing flow near the wall, the no-slip boundary condition forces the velocity at the surface to be zero. If we directly use the velocity field to draw wall streamlines, the result is often unsatisfactory. The streamlines become broken, discontinuous, or may even fail to appear at all. To solve this problem, and to mimic the oil flow visualization used in wind tunnel experiments, I use the shear stress vectors instead of velocity vectors. This works because the direction of the shear force reflects the flow tendency of the fluid right along the surface. As you can see, with this setup, we can generate very smooth and clear wall streamlines. This allows us to intuitively capture the near wall flow speed and the formation of the curved streamlines around the wingtip. At this point, the flow field analysis is already sufficient. If we now want to apply these aerodynamic loads to a structural solver, such as a Bacchus for fluid structure interaction, FSI, how should we proceed? Depending on the complexity of your model, there are two standard approaches. The first case is when you model the wing in a Bacchus using simplified 1D beam elements. In that situation, you don't need detailed 3D contour plots. Instead, what you need is the resultant force and moment generated by each wing segment. In star CCM, the threshold function is used to subdivide the wing surface into several independent strips. For each strip, a force report and a moment report are defined. In this way, the continuous pressure distribution on the wing surface is integrated into a set of discrete, equivalent point loads. When a finer discretization is required, for example, more than 10 strips, the process can be automated using star CCM built-in macros equals Java, or by coupling with external Python scripts for data extraction and load transfer. The second approach is a higher fidelity method. In this case, we assume that a full wing model has been built in a Bacchus, including the skin, spars, and ribs. Here, the simplified beam model data is no longer sufficient. Instead, we need to map the entire surface pressure field onto the structural model. We can directly export the wing-related region from star CCM. The exported data includes the pressure and shear forces of interest, which together represent the aerodynamic loads acting on the wing. If the aerodynamic simulation software, such as star CCM, and the structural analysis software, such as Abacus, use the same mesh, then the process is very simple. You can import the data directly. However, if the meshes are different, then Python is needed to interpolate and transfer the CFD mesh data onto the FEA mesh. Abacus does provide built-in tools for mapping reconstructed data, but I'm not certain whether it can correctly read non-scalar fields such as wall shear stress. So in any case, we can always use Python to interpolate both the pressure and shear forces and restructure them into the format required by the structural solver. I will demonstrate this process in a future video. Thank you for watching. I look forward to your comments and suggestions. See you in the next video.